Okay, I'm going to do a video on another microcontroller, and this is it right here. And as you can see, it's a little bit bigger than the last one. It's this one right here. Oh, the lighting's terrible, I know. So this is a 14-pin microcontroller made by Microchip as well, just like the old one that I did. And yeah, the other one was about 15 years old. This one's much more updated. It's from 2019, and it is an 8-bit microcontroller as well. Out of curiosity, the difference between a microcontroller and a microprocessor, which you find in usually most computers, is that these have very limited number of instructions. Actually, there'll be like 50 instructions that you can use to control this microcontroller, whereas maybe a microprocessor found in a computer might have 150 or 250 instructions, so a lot more to learn. These ones obviously are more complete. They have a lot of things inside here that a microprocessor will not have. It'll be the other chips all around the microprocessor, which will allow it to work. So this one will have an internal oscillator, internal memories, banks of several sorts. It'll also have several peripherals inside there to control serial communications, or maybe analog to digital communications, or yeah, comparators, tons and tons of things. Matter of fact, there's a 700-page manual on how to make that thing run properly. If you want to use all of the peripherals, but in which case we're not going to. We're going to do a really simple video on just a basic program to make this LED right here light up. This one has a little 200 ohm resistor attached to it, but I'm going to just put the whole thing on a little breadboard like that with a battery. And just to make it a little interesting, I will add a push button so you can see a little bit of input working, not just an output. This is your most basic program that you can get. It's usually called a Hello World program, so you can see if you can figure out how to make that thing work, which is kind of complicated because sometimes trying to get the program into the chip and have all the hardware shake hands is a little frustrating at first, the first one you build, that is. But that's what we're going to do today, and it's going to be an unstitched, unedited, front to back full video with no stops. So it's going to be hopefully only about 25 minutes long. We'll see. Anyhow, this is a programmer right here. I programmed this chip with my Windows 10 based computer, and it plugs in with a USB port into this red box here. This is a PIC Kit 3 as they call it, and you get it from Microchip as well, or maybe Amazon. And I just put a breadboard on top of it. So I glued that on there because I wanted to put my chip on the top of this, and I will do that right now. And obviously I've got a bunch of wires running to it, and these wires are wired in a certain way that you can actually get the instruction manual for this, and they just tell you how to do that. I've obviously plugged 4 more batteries on the back, so I get 5 volts roughly, so that I have a 5 volt connection here so that it will program properly. And I'll just plug that into my computer through the USB port main cable that was provided with the PIC Kit 3. Nice and simple. Like I say, that's 25 bucks. These little microcontrollers are $2. I usually buy like 40 at a time because I figure if I'm going to read a 700-page manual, why would I buy one? Anyhow, I did print out a few of the documents from the 700-page manual that is called a PIC 16F18424 or 424 data sheet is what they call it. It's free from Microchip, and I'll just briefly go over a few of the things that I wanted to point out. Obviously on the introductory page, there's a whole bunch of information about what is on this chip, what it can do, how fast it can run, and it can run up to 32 megahertz clock speed, or virtually nothing, like right down to like DC or barely ticking along. And like I said, it has a lot of different things. It has timers built in. Yeah, pulse width modulators. Yeah, lots of things. I actually bought this particular chip because it had a 12-bit analog to digital converter, which I like. And also I like the size. 14 pins I can deal with. And it has enough memory. I think it has like several thousand bytes of memory that I can use. This is the pinout for that chip. And what we're going to do, I'm just going to briefly tell you what I'm going to do with this project. So this 14-pin chip, pin 1 is positive voltage, and pin 14 is negative. So it's roughly about 5 volts that I'll put on. Oh, actually, I'll put on 3 volts. 3 volts onto this chip. And the rest of the pins will be all digital input-output. I'll probably make them all output except for one I will use for the push button, which is an input. So in general, I think I'll put the LED on pin 13, between pin 13 and pin 14, which is 14 being the ground, pin 13 being, they call it RA0, which means port A bit 0. So when I control port A bit 0, I'll be controlling this light here, or this LED. I'll be putting a high or a low on that LED and turning it on or off. And this little push button, I'll be putting it on pin 2, between pin 2 and ground as well. So pin 2 is actually called RA5, which is port A bit 5. So when I read port A pin 5, I'll be reading the push button activity. And with this particular chip, you can program a pull-up resistor. So if you know anything about these little like microchips or processors, they usually want a pull-up resistor sitting on a pin that they're reading. And if you want to control it with a push button, you pull the pin down by pushing the button that connects to ground. So you're basically taking the voltage from that pin, this pin right here, and pulling it down to create a signal. So it's basically held up with a pull-up resistor, which I will program into that, because this chip offers the feature of programming a resistor in instead of having to get a resistor and put it on there. Fair enough. Anyhow, what else am I going to do? The instruction set. So this here, we're using assembler to program this. This chip can be programmed in either assembler or C, but we're choosing assembler right now. And it's a very simple language to learn. That's the thickness of the manual, the whole manual, all of the manual, right there. See that? If I get a book on C, which is the other language, it'll be that thick. Or maybe that thick even. And so it's much more complicated. This is very easy to figure out. Matter of fact, there's only 50 instructions. This is a brief explanation of the instructions right there. And this is more involved explanation. And it's called assembler because it's a very low level language, because it's basically talking the language of the processor, whereas C, or a higher level language, usually talks towards the conversation a person would have. The words are more associated with words that people would use. Higher level language is usually closer to English. Lower level language, closer to binary. And oops, what else? Yeah, that was about it. Yeah, roughly we'll do things like a go-to statement, maybe a call statement, maybe a return, maybe an adding statement or a move statement or decrement statements, a variety of them. You can see them all in here. Like there's a move W into file register, or move a literal into a W register. We'll be doing those ones as well. But yeah. Oh yeah, okay, so this microcontroller has a lot of information, and what they do is they put everything in banks. So when you bank to a certain area, you have the access of file registers in that area that will be associated with a certain peripheral. So for instance, if you are using the analog to digital converter, you might have to bank over to bank D, or bank, I don't remember where the analog to digital converter is, but it could be way down here somewhere. And in which case you'd bank over there and you would alter the registers associated with, well, that particular peripheral. And in which case we're going to be usually staying in bank 0 for most of our program, because it's to do with a digital I/O port. And we will actually go to start at the very beginning. We'll go to bank 3E because we want to program this chip to work as a digital chip. So I have to change this right here, ANSCLA. It's actually an analog select byte. and it's actually set up to have the chip work as an analog chip, but I want it to work as a digital chip, so I will zero out that entire byte, and that's for port A. And ANSELC is the analog select byte for port C. There's two ports here, port A and port C. Each have 6 bits in them, totaling 12 bits, and that's all you have is 12 I/O ports. And I'll be changing ANSELC to zeros as well. Curiosity, you can actually work your programming with 2 ways to call up these file registers. You merely select bank 3E, but you can call the register by a name, such as that, or you can call it by its register number, which is 38 in that case. Oh, also, right down below it, I'm going to program a pull-up resistor for my push button, and that's done with the weak pull-up resistor on port A, the one right below it, WPUA, and I believe I'm doing bit 5, so it's going to be that bit right there. I want to change to a 1. So yeah, oh yeah, and as I said, there's a handful of things in bank 0 that I'll be using, including the port A actually. There is no port B in this chip. This is a very generic sort of piece of paper, but we have a port A and a port C, and a tris A and a tris C, and a latch A and a latch C. And what these things do is, normally if you want to read your port, you read your byte that's on the port, you read it through the port bytes. If you want to write to the port, you write through the latch right here. Now this right here, tris, this here programs, or you program your I/O port as you want through this byte here. So if I want to put let's say I want this one to become a high, or I'm sorry, a input, so I will make it a high, and anything I want to be a output, I will make low. So a 0 on any of those bits represent an output, and a 1 on any of those bits will represent an input. Same with tris C. So you actually create your port with this byte, these 2 bytes right here, and you merely read and write on these 2 right here. And that's about it. So let's start to program the program. I'll do the data right now. So I'll simply turn this up to here. Oh, let me just fix my screen a little bit here. Wasn't quite ready to do this. I already had a bit of stuff here. Here we go. So about here, I think. That's where I want this. You're probably thinking, this is so low tech. And it is, I know. I won't deny it. That's not bad. Okay, so what we're looking at here is my Windows 10 based computer. And I got a free download from Microchip. And this is the programming platform. And it's called MPLab XIDE, and it's version 5.2. Since we're programming in assembler, the best version to use, they suggest, is version 5.2 or version 5.3. If you go any higher, right now I think there's version 7 or 6 point something out there right now. If you go any higher, you'll find that you'll have to accept several downloads, and it's more designed to run the C platform or the C compiler platform. It's not actually assembler friendly beyond version 5.2. You can get that for free in the archive section of the Microchip webpage. Anyhow, I will delete some stuff here just so it'll look like what you would get when you start off and you get your MPLab XIDE showing up on your screen. So it's roughly like this, and all we're going to do is we're going to start building our first bit of code, and this will be quick. Select File, New Project, and select standalone, next. And we have to try and remember what the chip was. And hey, there's like several hundred different types of chips Microchip puts out. And this one happens to be a 16F18424, but many of them run the same way as this one. And you'll find that the difference between this chip and yours, whatever it is, if it's relatively new, will be almost identical, except for maybe the port address where you have your LED will be different. Anyhow, that's good right there. Next. And of course, there's my pick programmer, pick 3 programmer. And there is my assembler I'm going to use right there. Next. I need a name for this project. I'm going to call this test 22. Yeah, that looks like what I want to do. And then that will create a file folder over here. See this file folder called test 22? There's several file folders. I want to get to the source file. Click left, click right mouse button, click on the new assembly file .asm. So I'm creating an ASM file. I'm going to call it test 22 as well, just because I don't have any creative mind here. I'm just running that way. Okay, so we still haven't programmed anything. There's no code yet. We're just doing setup, and it's pretty much the same routine all the time when you set up. Now we're going to actually create some, so what you have to do right here is the same thing. You have to do certain tasks first. Go to production, go to set configuration bits. So this processor, this microcontroller here, has several things it can do, and this is merely setting up that microprocessor so that if you want it to run at a certain speed, you can do so. If you want it to, so I'm going to set up so it runs at maybe 1 megahertz, and I'm going to turn everything else off to make it a nice, simple process. I'm not even going to think about it, I'm just turning everything off. A lot of these things, you should read up on them. Maybe you might want to change it. This one here is a brownout detection or protection. I don't care about it right now. I just turn it off. It might be useful for you. But I mean, some of these things like this one right here, the watchdog timer, if you don't turn that off in about 2 or 3 seconds, it will take your program back to the beginning. It's a weird thing. And a lot of these things, if you don't know what you're using them for, you don't want to have them on. It's best to have them off because it does run well without all the complexity. But a lot of those things are useful for the right person, like the brownout detection or protection, or the yeah, you can actually even configure this so you lock up your code protection so nobody can steal your code when you build something, and that would be in here. Anyhow, this is all programmed the way I want it. I'm going to generate some source code, which I'll put into my program. Click right down here. It generates that source code. And out of curiosity, you'll notice that there are some things right here that I'm not cutting out or copying out. They have a little semicolon at the front, which represents remarks. So remarks usually come right after a semicolon, and they are just things that you have yourself personally, and it does not affect the program. Okay, I'm going to jump over to my program, which is test 22, and tuck that code right there. Great. Okay, so I am ready to start programming. And what I've just done here is I've just tucked in one piece of code that said the origin of the code that will be on the chip will be at location 00. And after that, basically, I'm writing code. So finally, I'm at the point where I can write code because there's I've done all the preliminary stuff. So I'll explain what I'm doing here. I've left some space over on this side right here, a nice pocket of space, so I can put some labels down there. But yeah, let me just type out a little bit of stuff here, and I will tell you what I'm doing in a second. So what this is, I've just banked the program. When I say move literal into B, I'm actually moving the literal, 3E by the way, is the literal, into the banking register. And these are all called instructions right here. And they're obviously an instruction set of that 50 instructions that are available. And like, I'm only using maybe 10 of them in total. You'll just see about 10 that'll show up here in maybe about 20 lines of code. Anyhow, we just banked to bank 3E, which has the analog controller on it. So I've just cleared the analog controller from port A. That's what N-cell A is all about. And now port A will run as a digital port. I did the same thing here. I cleared the file register N-cell C, which cleared the analog selecting port for C. So now it's going to run digital. And what am I going to do next here? Oh yeah, so I also wanted to get a weak pull-up resistor. Remember that? A weak pull-up resistor on port A, bit 5. Yeah, so bit select file register WPUA5 did just that. Okay, so what else am I going to do here? Okay, so now I'm going to go back to bank 0. So move a literal into bank 0. So I'm now back at the 0 bank where I'm going to do all the rest of my stuff here. Give me a second here. So what I've done here, I've gone back to obviously bank 0, and I moved a literal, which is 20, into what they call a working register. And I moved the working register down here into file register tris A. So when you want to get a number into a register, you usually put it into a working register, and then you drop it into here. There's no option to actually take it straight into here. It's a problem with obviously an 8-bit processor will not have the capabilities of doing a multi-job like that. Anyhow, if you notice 20 in hexadecimal is actually equal to, what is it? Something like this. Yeah, that's 20. And that you can see when I'm tossing that into tris A, that 20, that is going to make bit 5 a 1 right there. This is bit 0. 1, 2, 3, 4, 5. And the rest will be all zeros, which will represent all outputs. So there's one input for port A and a whole bunch of outputs. Okay. And I will do port C as well. I don't need to do port C, but it's just for consistency for you guys, just to let you know that it's something that, and actually I could even reduce this instruction set. I could remove this command and make it different. I could just say clear file register tris C, actually, isn't it? Yeah. But I'm just going to put the 0 into the working register and drop the working register into there. But I could have just cleared that and it would have done the same thing. But yeah, you can always write your code many different ways, and I'm just doing it that way. Actually, you know something? Now, right here, I'm going to put my first label, and it's going to be called start. It could be anything you want. I've decided to call it start for some weird, unbeknownst reason to you. And I'm going to explain what I'm going to do here. So, what I'm doing here is I'm creating a trap. So what I'm doing is I'm trying to make it so that the, I just want to double check my camera is working. It's a smartphone. So what I think I'll do is I get my push button will be the gatekeeper in front of the LED light program. So normally the LED would flick off and on, but to test out a button, I'll put the button at the front, so you have to push the button in order for the light to work. So what this bit of program does right here is it says bit test file register, and skip if clear. Since I have a high on that port from my, my pull-up resistor, it will look at port A bit 5 where the push button is, and if it's a high, or if it's a clear or low, it would jump over this here, down to right there. But since it's actually going to be a high on it until I push the button, it's going to continuously loop around here. It'll be going back to start, or back to this label here. So this will be basically going around in circles until I finally push that button, and then it will drop down to here because finally it will skip when it sees a clear, which is what it just did when you push the button. It grounded out the high signal. And at that point, I will do my next bit of code. So what I'm doing here is I'm actually turning off the light right here, bit clear file register latch A, port A, bit 0. And then over here it's bit set file register latch A, port A I should say, bit 0. So it's going, the light goes off, the light goes on. And if I do a return right here, or a go to anyhow, go to start. You can see that right here, after it's gone through here, it'll go right back to start and it'll continuously go around in circles as long as that button is pushed. And you'll have the light going on and off. But there's a problem here. When the light goes on and off, it's actually, this processor crushes code at about 250,000 instructions per second. And that's at 1 megahertz. So it's flicking on and off so fast I can't even see it. So I'm going to put a delay right here. I'm going to call a delay that I'm going to create in a second here. Call delay. Oops, let's learn how to spell. Yeah, call delay. And I think I'll call delay right after I turn the light on too. So and then it'll go down here. So I'm going to build a delay right here. Let's go right over here. And we're going to call it delay, obviously. And I'll build a little bit of code here. Give me a second. I'm just recovering from COVID, by the way. It was about a week and a half ago. So, decrement follow. So what this does is I decrement a file. Okay, this is decrement file register skip if 0. So it's going to decrement file register 20, and the 1 just means it throws it back in it. It'll decrement file register 20, and it will skip the next line if it's a 20, if it's a 0, I mean. So obviously it'll probably loop through here 256 times until it finally gets to a 0. At which point it'll finally skip down to here to the next piece of code. So this is a way of delaying time so the light can be seen to be off or on. And it's going to be called a nested loop for a reason. Because it basically is a loop inside a loop. This thing twirls around 256 times. Drops down to this next one, which decrements file register 21. And by the way, this particular processor in bank 0 has about 80, maybe 80 general purpose registers from 20 up to I think 7F. Can't remember if that's 90 or so. Either way, this is going to loop around 256 times, drop down here, and decrement that one, and you'll realize it has to loop through here 256 times as well. It'll generate like 65,000 loops until it finally gets a return command by following through the loop down to here. It'll return from where it came from, up here somewhere, right to the next line, obviously. And that's my program. So spaces are fine. I just throw a space in there for the fun of it. I think that program's complete and it's ready to roll. Yeah, you should put remarks all over the place. It's good for you. Just so you can see what your program's doing. It makes sense. So when I want to build this program or compile it or assemble it, whatever you want to call, you click on the little hammer and it comes along and it checks and it says it was a build success. That's good. So then I want to install it into the chip, and I push this little button here to do that. There you go. So now it's installing the program into the chip. As you can see, it's said it's programming, verify, and complete. So that's what it did. Okay, so that's good. So let's have a look at this this little chip that we just finished programming. And I'll just put this camera right down here without hopefully dropping it. It's on a little tripod, you know. So that's about right there. Oh boy, is that? That's not bad. Okay, so there's the chip that I just programmed that's attached to my Windows 10 computer. I might as well just pull this out of here. And I'll pull the chip out of here. I'll just put it right in here. Okay, so what was it? I said I'd put the little light over here somewhere. And I think I was going to put my switch over here on pin 2. And of course to the ground right here, which is right there. Okay, so it's terrible lighting here, but that's fine. Okay, so let's see what we got here. Works fine. So while the button's pushed, the light works. And while the button's off, the light stops. Yeah. So that's the project. I hope you enjoyed that. I hope you get out and try this project. Like I say, there are only like $2 a piece for those. Thank you for watching and enjoy. Subscribe.